So we set up the scene in the previous podcast about how the different regions of the Indian subcontinent have these interactions. So annual lightning frequency gives you a sense of the WD region, and this is of course the monsoon region. But now we are going to talk about WD interactions with the monsoon and how they happen. Extreme rain, so this is interaction of WDs with the Indian summer monsoon ISM. Extreme rainfall events associated with WDs can be catastrophic. These negative WD impacts most commonly occur near the beginning and end of the ISM, pre and post monsoon. Well, beginning and end of the ISM itself, not pre and post monsoon. When southward excursions of the subtropical jet results in embedded WDs interacting with moist monsoonal air masses, strong southerly moisture flux, and large regions of ascending air associated with these WDs create favorable conditions for intense convective and orographic rainfall. And there are some examples from 1988 in Punjab, 1992 Northwest India, Pakistan, Uttarakhand 2013, Kashmir 2014, and so on. WDs are most, so we will look at the synoptic picture in a minute in the next figure. WDs are most commonly associated with the winter months when the subtropical westerly jet is furthest south. However, they can occasionally occur during ISM, June to September, either due to the southward excursion of the jet or as elongated digging troughs and cut off lows. So these are terminologies people use. Perhaps the most notorious example occurred in June 2013 when a WD interacted with a monsoon low pressure system, LPS, we referred to before, resulting in devastating floods over Uttarakhand. Other cases have been noted with Uttarakhand and Himachal Pradesh seemingly the most common regions impacted. So when we say WD and LPS interacted, those are very hard to predict. Even though you may be seeing a WD coming along, LPS coming along, the forecast may not see them interacting and producing these disasters. Nonetheless, they are lessons to be learned anyways. Majid et al. Showed that floods in the Indus Basin in September 2014 were linked with the accumulated effect of several WDs interacting with the summer monsoon. WDs can also interact with tropical storms outside of the monsoon, such as a case in October 2021, which led to record-breaking rainfall in parts of Uttarakhand. So we are obviously talking about events rather than a process that repeats itself, and obviously that makes them harder to predict. But understanding the processes obviously will help with predictions as well. But as we will see later, right now WD's prediction is not at all very good. Okay, so we are looking at the 1988 event here, 1992 September, and this is June 2013, and you can see the similarities of the monsoonal circulation, because these are the end of the monsoon and the beginning of the monsoon. So this is 200 hectopascal wind in the green color, and the vorticity at 350 hectopascal in the magenta color here. You can see the overlapping advection of vorticity, and vertically integrated moisture flux being shown in arrows. So you have massive pumping of moisture from the monsoonal circulation interacting with the winds and potential vorticity, giving you these bullet points of daily precipitation in the range of these dark blue colors are over 100 millimeters, which typically, depending on how quickly it happens, can be deadly. Okay, and combined with the slopes especially. Synoptic charts of 3 cases of severe flooding associated with passing western disturbances: the 1988 Punjab floods, the 1992 India-Pakistan floods, the 2013 Uttarakhand floods. Charts are shown for the day on which the heaviest daily precipitation occurred. Green barbs show the 250 hectopascal winds, where they are in the top quartile of the domain shown. I hope you know how to read these. Winds are coming in this direction, and these barbs show the magnitude, so they can be like let's say 10 meter per second, then it will be 30 and 40 and so on. The scale is not quite given here, but we'll read in a minute anyway. Okay, so you can see the fronts as well with these dark green triangles. Charts are shown for the day. As we said, green barbs show 250 hectopascal winds where they are in the top quartile. Black arrows show vertically integrated moisture flux, as we said, and magenta contours show positive 350 hectopascal relativity in intervals of 5 times 10 to the minus 5 per second, all computed using ERA 5 reanalysis. Colored contours show daily UTC, daily 3 to 3 UTC precipitation from Aphrodite gridded, so you have precipitation. So gives you a sense that interaction of the monsoonal fluxes with the western disturbances can produce hotspots of heavy rain in the suspected regions of the Himalayan foothills. Okay, so let's look at another one here that is moving ahead on how tropical depressions, low pressure systems can interact with WDs as well. This is from Hunt's paper from 2021. Schematics for each of the major types of interaction between WDs and TDs, tropical depressions. Vortex merger occurs when vorticity anomalies associated with the WD superposes that of a TD. So you have a path of a WD coming in here with its cyclonic vorticity and path of a TD coming in, and they end up interacting with each other and producing heavy rain. And the second one is when the jet streak excitations occur with tropical depressions being simulated through quasi-geostrophic forcing from a streak enhanced streak entrance region associated with a western disturbance. So that's here. So you have a jet streak and you have a low pressure system or a tropical depression coming in, and that is interacting with the jet streak, and there is a WD sitting here on the other side which is also interacting with the jet, and together you are creating conditions for heavy rainfall. Okay, these are kind of typologies. Are they always predicted? Of course not, as we will see in a minute. C is tropical depression to WD moisture exchange occurring when net moisture flux passes from tropical depressions to a western disturbance. So you have tropical depression with its cyclonic circulation carrying moisture. They again add about 60% of the rain, according to most estimates, to the mean seasonal rainfall. So they are, especially during active periods, they are covering this entire range. And there is a WD with its ascending and descending branches on the east and west, and you have moisture being supplied to the ascending branch from the moisture flux associated with the tropical depression or the low pressure system. And in D you have the other way, where a WD is supplying moisture to the tropical depression. So it has picked up moisture, let's say from the Arabian Sea, and with its counterclockwise or anti-clockwise circulation, it's pumping in moisture into the approaching tropical depression or low pressure system. There are all kinds of interactions proposed. I have just recorded a podcast on how the Rossby waves from the North Atlantic are also able to create secondary cyclonic vortex and LPS interaction to produce large scale rain events, but here we are only talking about WD-TD interactions in this limited context. So somehow we come back to the definition of western disturbances. Then the formal definition of WDs published by IMD is weather disturbances noticed as cyclonic circulation or trough in the mid and lower tropospheric levels, or as a low pressure area on the surface, which occur in mid-latitude westerlies and originate over the Mediterranean Sea, Caspian Sea and Black Sea and move eastwards across North India. Much of the research presented in this review shows that this definition is now outdated and has led to authors using their own criteria, the authors of many papers including this one. To aid consistency and reduce ambiguity in future research, we synthesized the research discussed in sections 2 and 3 to create a new and up-to-date unified definition of WDs, and this is a new paper, so you have to then see if other authors accept this and how long this definition will be used, or whether it will become a standard and so on. Western disturbances are eastward traveling upper level troughs passing over South Asia that arise as instabilities on the jet or as extratropical potential vorticity cutoff lows. So potential vorticity contours can produce like a little eddy that cuts off and becomes a low or a cyclonic circulation system that then becomes identified as a WD. By drawing moisture primarily from the Arabian Sea, they bring precipitation and sometimes other impacts primarily to the western Himalaya, Karakoram and Hindu Kush, but also to the surrounding regions of Pakistan and North India. They can occur at any time of the year but are strongest and most frequent between December and May. And the definition of a particular feature is so long, you know that then it becomes very important that we find a way to track them and identify their life cycle, their pathways, their frequencies, their densities, and so on, so that eventually you can get to predicting them and their impacts. Moving on to large-scale forcing and teleconnections, again I'm going to be very brief. So we are just jumping ahead. Therefore, there are many subsections. Therefore, there is high confidence, robust evidence, medium agreement that WD frequency and intensity increase during positive phases of the NAO, North Atlantic Oscillation, but low confidence with limited evidence and medium agreement that WD frequency increases during El Nino. So the discussion has already happened about how large-scale forcings like North Atlantic Oscillation, Indian Ocean Dipole and El Nino interact or affect WDs. There is forcings affect WDs, that's why they are called forcings. There is very high confidence, robust evidence and high agreement, however, that winter precipitation is greater over western Himalaya during El Nino. So El Nino is peaking in DJF, December, January, February, which is the peak WD season as well, whereas the monsoon is peaking in June, July, August. So there is a phase lag. So we have to figure out all those things. IOD happens in September, October, November. So again, what does that have to do with? Excuse me. My throat suddenly got dry. Okay, so winter precipitation over western Himalaya during El Nino is great. Is greater. There is very low confidence, limited evidence, low agreement that positive IOD increases WD frequency. Because some papers have claimed this, and obviously there are not always enough statistics to claim this. Nonetheless, I skipped. This was 14. Yeah, we looked at 13 and 14. So let's move to 15. There are lots of figures. It's a review paper, but it's long even by the standards of a review paper. Correlation between seasonal mean sea surface temperature and WD frequency computed for winters, so November to March between 1950 to 2021, to get a sense of the remote and large-scale forcings. Stippling indicates regions where the correlation is significantly different from 0 at 95% confidence interval. Green labels indicate where large regions of significant correlations correspond to known modes of interannual and interdecadal oscillations, with plus and minus indicating positive and negative correlations respectively. Areas of interest are the North Atlantic Oscillation positive correlation with this box here where we are looking at WDs. PDOs has negative correlation. So the colors are here in the range, and this is the southern annular mode. So, and that has negative phase. Basically, that means positive NAO phase, negative PDO phase, and positive SAM. So, positive correlations with NAO, negative correlations with PDO, and positive correlations, because positive and negative indicating positive and negative correlations respectively with WDs here. Areas of interest are, as I said, North Atlantic Oscillation, PDO, and Southern Annular Mode. The red box indicates the region in which WDs are counted using ERA 5 derived tracks, SST data from HADA SST, and so on. Okay, there is also a signature here which is now being looked at as some zonal or meridional pattern in the southern Pacific, which has relations with El Nino, but you can see WDs here show no correlation with El Nino, even though this is approximately in the tropical region which extends, just remains mostly south of the equator, but it's significant only here. These stippled regions are where the correlations are significant. Okay, do what you want with it, but eventually you want to understand the mechanistic links as to how WDs, is it that these are affecting the jet and hence WDs, or is it something other process, winds, vorticities, moisture loading, and so on and so forth. There is some discussion on modeling and forecasting. I will just be very brief about it. Model evaluation and verification, reading just a little bit. Three important questions remain unanswered by this earlier research. So they have had a section on earlier research already, which I skipped. How good are climate models at representing WDs and their statistics? What can be learned about the structure of WDs and their interaction with the environment from high-resolution convection permitting models? How important is the choice of convection scheme in simulating WDs? In the next subsection, we'll discuss how recent research has tackled these questions. So we will look at the new developments here, then jump. I will focus a lot on the questions that remain for future research, because that gives us a full sense of what is known and what remains to be understood. As with previous research, recent developments fall into two categories: testing model sensitivity to the variation of empirical parameters, initialization datasets, and data assimilation. And secondly, evaluating model capability either in numerical weather prediction or in climate frameworks. Numerical weather predictions tend to be higher resolution models but forced with prescribed SSTs, whereas climate frameworks are typically lower resolution but fully coupled ocean atmosphere models, and so on. There is thus high confidence, robust evidence, and medium agreement that simulations of WDs are mostly insensitive to the choice of parameterization scheme, but also high confidence with medium evidence and high agreement that the choice of land surface scheme is important. So somehow land atmosphere interactions seem to be important. Parameterizations, you have to go back and see whether that's just convective parameterization or something else. There is very high, typically it's convective parameterization, there is very high confidence that WD simulations improve with increased model resolution. Okay, obviously cyclonic systems of small scale and the interactions with the jet are probably better captured when there is sufficient resolution. Forecasting is looked at with short and medium range, but here are the summaries. At present, there is thus at present very low confidence that WD tax can be skillfully forecast in operational models at any lead time. So if we understand all about WDs and you can even watch them coming and you cannot forecast where it will go next, then the forecast is not very useful in terms of preparing for floods or landslides, whatever else fog and impacts on glaciers and so on and so forth. The following are some preliminary observations from the IMD system. IMD's day zero warnings essentially serving as nowcasts tend to align well with the GPM iMerge, especially with as these warnings pertain to heavy rain or thunderstorms. So you get some warning, but it's very short. Risk forecasts are generally accurate up to lead times of 3 to 4 days, even in regions with complex orography. So you have to go back and see what risk means in this context. However, it could be risk of high rainfall, hailstorms, and so on. However, the general tendency is for warnings to escalate in severity as the event draws closer. So, shorter term forecasts are more robust. While this approach minimizes false alarms, rapid escalation of warnings challenges a timely and effective response. This happened in the 7th January 2022 case in Ladakh, where a yellow warning the day before the event was upgraded to a red warning on the day itself, but often by then it's too late for people to get out of the way of the harm. There exists an inconsistency between IMD's high-resolution nowcasts produced using radar and satellite products and their day zero warning bulletin maps. Such disparities can lead to confusion among stakeholders, but we have to see more carefully what exactly that is. Okay, so here is a warning bulletin issued by IMD for 4 recent dates associated with severe WD weather. For each date, warnings issued up to 4 days in advance are given in the first 4 columns. So day -4, -3, -2, 1, the day of the event, and it's talking about dust storms, strong winds, thunderstorms, visibility issues for flights and so on, heavy rainfall events, and you can see they can be all mixed as well. And daily precipitation in millimeters are shown here in the product GPM iMerge, which, if you want what that is, global precipitation measurement was a satellite mission, integrated multi-satellite retrievals for GPM. That's what it stands for. Okay, the IMD describes the warning colors then as below: green, no warning, no action needed; yellow, watch, to be updated, keep alert; orange, alert, so you have to be prepared; and red, warning, which means time to go and take action. Areas marked in gray in the GPM iMerge panels indicate where data are currently unavailable, so you can see large gray areas. All bulletins were taken from the official web page of IMD and so on. Basically, the issue also is extracting precipitation from satellites in very complex terrain with mountain ranges is very difficult and uncertain, but nonetheless you can see that there are some skills in them. This is adapted from Arulalan et al. Tracks of 3 WDs identified in the NCMRWF, so that's the National Center for Medium Range Weather Forecasting of India, between 1 and 10 February 2020. The dotted gray rectangle indicates the capture region. Here you cannot see it clearly, but that's the same box we saw before. The box through which tracks must pass through to be detected. B are the tracks of the same 3 WDs identified in the 23 members, including 1 control member of a 10-day forecast of the NCMRWF ensemble prediction system initialized on February 1, 2020. The thick black line is a smoother 2 kilometers. So you have the orography in this here, and you have the track of track 1 here from February 1 to February 4th, track 2 February 3 to February 10, that's in the yellow here, so obviously it goes back longer, and track 3 February 6th to February 9th, it's down here. So they have to pass through this box to be detected, and this is the ensemble prediction system, 10-day ensemble forecast, all initialized on February 10, 2020, and you can see again different periods as above, but basically some kind of a perturbation to the initial condition is used. You can see they are starting all from different places, but they are mostly going through here, except these few that enter the box and then they go off. So just remember what we said here, that at present very low confidence exists that WD tracks can be skillfully forecast in operational models at any lead time, so which means nowcasts, which is basically about extending available near real-time forecasts to the next few hours, is the best option we have, which makes it a very short lead time forecast and can be useful in many ways, but sometimes it can be too late. So this is the probability of WD center passing within 400 kilometers of the box. So you are again looking at initializations at different time periods, and the point here is operational forecasts of WD track location from 16-member IMD extended range ensemble forecast for a WD impacting the Western Himalaya on 13th March 2015. Each panel represents a different initialization date with tracks from the ensemble members given by thin blue lines and the ERA 5 track given by a thick blue line. Filled contours, so you basically look for skill. And the closest initializations are on the bottom right here. Okay, that was the track, and then you got it right in some cases. Extended range is basically weeks 2 to 4. So you want to be very good at 1 to 3 days, 3 to 10 days, but also be good at weeks 2 to 4, because that's where a lot of the decisions can be made as well. But then, as we saw before, there's the track prediction skills seems to be very low at all time scales. I'll leave this here and we'll come back and look at the details of this figure, because the paper has a lot of discussion on the WDs through climate, WD variability with time, and it's looked at the Holocene level for different periods. I'm not going to go into it, but we will look at this figure just to get a sense of what points they are trying to make, and then you can follow up in the text, but we'll also look at this table to get better sense, and we'll basically see whether the trends in WDs, that's a big debate whether there is a trend or not, just like in the low pressure systems as well. So I'll come back and look at all these things. I don't know if we'll be able to wrap it up in the next podcast, but it's okay. We'll take one more if necessary after the next one. Okay, so let's come back and discuss further.